All right, let's continue our talk. Well, it's unlikely I'll finish this lecture. All right, let's go on, move on to see what's going to happen. All right, we will close the session at 9 sharp. Okay, don't be late because I'm hungry. I have not had my dinner yet. Okay, you don't want to see your professor starving to death, right? All right, and this is what it's supposed to look like. I will call this a cell concept, or you can call this a floor plan. When you want to talk to your, you want to, make a plan, make a project with your friends, you have to find out the common sense for this part. Okay, well, what do you like together? Okay, how do we place all the parts, and then we can use it, reuse it. Let's assume one thing. If you like to have a buffer, okay, just like the one I assigned you to do in your homework. A buffer is composed of four inverters, right? Maybe 8, maybe 10, maybe 1,000. So all you need to do is after you do the layout, somebody does the layout for you, and all you need is to take that layout and duplicate it, and then cascade them together as many times as you like. That's all. As long as they are positioned like this, then the output will go to the next. Inverter if the input power is placed like this one, and you can cascade them together, okay, immediately without any problem. All right, this is how it works. That's called the cell concept. You got to follow the rule, or you have to follow the rule that you can. Excuse me. Whoops. What the hell is this? All right, okay, good. So we are in business. All right, and this is how to use this kind of cell concept design. See, this is a NAND gate, and this is the inverter. And let's assume all the layouts are good, okay, after it is verified by the DRC, obviously, and ERC that we talk about. Then all you need to do is just copy them and put them together. And see that we have a short circuit automatically. And all the power supply are shorted, same as the ground. Then you have a layout automatically. I guarantee the work because I worked this way for 30 years. Okay, this is how you do the design. That's for the OR gate. So the complicated gates, logic gate cells, is equivalent to combination of basic cells. So all you have to do the polishment is that you only have to do the metal one layer. That's all. And this kind of design is called the hierarchical design approach, right? So first thing first, you gotta have the fundamental cells for your design, for your project. All right, this is the cell concept. And then let's do the step by step and make it efficiently. Okay, this is step number 1. If you don't like the stick diagram, fine. Okay, so this is how you do the design. First thing first, you put down the power rails. Power rails means that you have two parallel metals. Okay, one is in the bottom, stands for the power, stands for the ground. The other one is on the top. It is for the VDD power supply. Then you need a big well because this is where the P transistors you need, okay, where they are. So you need a big well, all right? And this is the distance between the M1 and M1. So the N well, okay, is sitting next to VDD because you need a well contact there. And the P substrate region is close to, is right next to the VSS. This is the PMOS because you also need a well contact over here. So power supply wires always goes first because power is everything, just like our life. Okay, energy is the fundamental of everything. Without energy, we'll be back to the Stone Age or Dark Age, all right? But this is another side note that Taiwan is an island. Taiwan is a country that 99% of the power, the energy comes from outside. Okay, we don't have a natural gas. We don't have petroleum. Okay, and all the geology heat is not reliable. Okay, we are not talking about a volcano, all right? Because a volcano, you cannot control that. And then we also don't like nuclear power because we cannot, we don't know how to deal with the remains after we use the nuclear power. So that's a problem. And the only thing that is reliable, a little bit reliable, is the hydraulic power. But right now we are short of rain. Okay, do you remember when was the last time Kaohsiung has a big rain? Let me tell you the number. It's over 550 days. We are facing the drought problem here. Water shortage very soon. Okay, so that's pretty pathetic. And basically, the bottom line is that Taiwan is an island short of natural resources. That's hard. That's hard. It is really hard. So I'm not the president of this island. I don't care, and I'm just a poor but a proud professor to just barely survive. But those guys in taking charge of the entire administrative building, they got to do something about it. And without the power, our life is black, totally dark. Okay, it's going to be very pathetic. Okay, too bad. And the green energy. I'll tell you the true fact, okay? The green energy, is it important? Yes, it is. But can we afford it? I don't think so. Do you know what is the ratio between the green energy and the nuclear energy? It's 3 to 5 times. 3 to 5 times. Okay, are you willing to pay that bill for the green energy? Are you? I don't know. Maybe you are. Okay, but green energy, including the solar power, including the wind power, and geology power, but they are not that reliable. All right, and the natural gas, the problem is we have to import every drop of it. That's hard. Okay, that's very hard. Okay, anyway, that's enough complaint. All right, next thing. Okay, let's go back to our design. There are 2 types of layout for the transistor orientation. Okay, you can select either one of them, but do not mix use of them. Mix up. This shows the direction of the currents. If all your transistor, you like the current goes through up and down in the north or south direction, vertical direction, that's fine. Okay, so if you line up this way, currents goes up and down, up and down. And you can rotate by 90 degrees. If you design your cell this way, this way, the current goes to left to right or right to left. Okay, that's fine. But please do not use this part to combine with this one. That is disaster. You see what I mean? Okay, either way is fine, but you don't use the vertical direction of the current and mess up with the horizontal direction of the peak current. That will be disaster. Okay, that's the rule number 1 for your orientation of your transistor. You select one of them, that's fine. Most of the cases, I prefer students use this one because it's easier to do your layout and have a better floor plan, okay? Because this will tell you one thing. Okay, I'm going to erase this one, right? It's not explicitly addressed in the textbook or literature, but according to my experience, if we consider that the cell is a box, a cell is a box. The cell is a big box. Basically, this is what I told to my students, because this is a box. The signal flows goes this way. This is the signal flows. Go this way. Input to output, okay? And this direction is a control signal. Control signal. Controls. Okay, in this direction. This is how I tell my students, okay? You can change the direction, but that will make your design a lot bit easier, okay? The control. Control signals are perpendicular to the signal to be transmitted or to be processed. Okay, you're gonna see a lot of examples like this one. And this way stands for the control in this direction, and the signal goes in that direction. Okay, it almost fit what I meant here. Okay, but this is not a rigid rule. It is just a rule for most of the cases. Okay, it's a box of a cell, and you like to, make the signal flow in one direction, and the control signal goes in the perpendicular direction. All right, this is just some guideline. All right, and these are the example to do that. See that? This is the input coming from the left. Output get out from the other side. And these are the control signals here. See? The same. Input, output, and this is the control. These are the controls over here. All right, and we are going to talk about the so-called, what does that mean, the wiring channels? Okay, we'll talk about that later. So this is the placement of the ports. Because if we have this in our mind, then we have the picture where these ports are. Okay, the signal flows, and those ports for the signal flows will be placed, okay, on left and right. And for those controls, they will go up and down. So you know where to place your ports, okay, your ports. This is for ports placements. Okay, channels. Okay, channels is important, okay? After you come up with your design, and there is a strict rule for that, is that the height of each cell must be identical. So you see that? Okay, no matter how wide or how narrow they are, but the height must be the same, so that it can put them together, okay, directly, all right? So the height must be the same. So we have a group of cells, they are sitting together on the top. Okay, they do a lot of processing over there. We have another group here. They also do a lot of jobs to process some signals flowing in these directions, all right? And some control signals, they would or they should share together. And we need some space in between. It's called the routing channel. Routing channel. The channel is meant to, draw these control signals over here. You can consider this as a free space. Okay, just like what? The building of this one, this is the building, and another building over there, okay, this is another building. And we gotta have some space in between so that the cars or the bicycles or the pedestrian can walk around. Okay, this is called the channels over here. We have some signals that these signals must be shared or communicated with each other across these buildings, across these blocks. So it's called the routing channels. And then there are some interesting things over here. If we put these buildings or these blocks too tight, okay, so that there is no space, just like over here. So it will become too crowded that signals cannot be, for example, I would like to have a control signal shared by these two blocks. Then we have a problem. Okay, we don't know how to make them short circuit together. So you have to get outside and come back and take a detour. That will be a long one. All right? And it might jeopardize other connections. That will be bad. All right? So this is one thing. So we got to give enough freedom to, to share these control signals. But if the freedom is too big, the channel is too big, we're going to waste a lot of space, we'll waste a lot of areas on the silicon. That is also not acceptable. So there is an interesting thing. How do we make sure that the channel space or the channel design is good enough to accommodate all the signals that we need? So here comes another problem. It's called the channel routing. How to route these signals and efficiently, so everybody's happy and no extra space will be wasted, right? This is called routing channels. So this is a definition of routing channels. Okay, we stop here, so for you to understand. Is that clear? So after you develop your cells, then we put the cells together. We might need other spaces for the control signals to go through these buildings, these blocks, okay, freely. All right, it's called the routing channels. All right, okay, and this is called the Weinberger arrays. Weinberger arrays is that if we don't need the channels, okay, if we don't need the channels, let's assume we have a very tight and compact design already. So the Weinberg, okay, they say that all the blocks, all the buildings, they can be flipped together. Why is that? Because if we have a group of cells, the VDD is on the top, the VSS is on the ground, and we find out that they don't need any channels in between. For the next one, we can flip it over, reverse it. Okay, reverse it so that for this group of cells, the VSS on the top, VDD on the ground, so that these two buildings, these two blocks, they can share the ground together. That will save you some space. Okay, let's go back to the usual design. Over here. So this is a traditional design. Let's assume there is no control signal to be shared. VDD, VSS, VDD, VSS. According to the DRC rules, we got to have a minimum space in between, right? So Weinberger suggests that we can flip this one. Flip this one, make the VSS on the top, VDD on the ground, so that VSS can be shared with the top one, and VDD can be shared with this one, so that we can save some space. That's the idea. Okay? So we can do that interleavingly, okay, to save some channel spaces, given that there is no requirement to share signals. Is that clear? All right? So this is Weinberg arrays. Okay? That's for you to make a reference. But according to my experience, rarely design, only a few design, very rare, few design where you take advantage of this part. Okay, the size. Size does matter. This is quoted from the movie Godzilla. Size does matter. Okay, let's take look at two examples. All right, these are two transistors. Two transistors, right? Two transistors. And remember that we have a surround rule and exact rule for the contact. Because this is a diffusion. There's a metal one, this is poly, and there is a strict rule for this contact. Strict rule for this contact. So it gotta be W over here. This is 5 nanometer. There's a minimum space in between. Minimum space in between. So this is what we picture here. All right. The minimum size. But if we follow the minimum feature size of a given process, we can make it smaller, like this one. Make it smaller than this one. So the width is a little bit smaller. Okay, both of them are well-defined transistors. They also comply with the rule of DRCs. Okay, DRC rules. But the thing is, if you look from the top view, basically they use the same area on the silicon. See that? Because you need, this is minimal size. You cannot make it smaller. So basically, this is the box area you need. This is another one. They are identical. Since the area is identical, which one will give you a better current or bigger current? The left one. Because the width is W over there is a little bit larger than here. All right? So the left one will be faster, will be a little bit more power hungry. Okay, but the area that you use is the same. So the bottom line, when it come down to the selection, which one you select depends on what your design goal is. The area is the same, but the one in the left will give you a faster solution. This one will be slower, but this one will be a little bit more saving power. That one will be a little bit power hungry. So it depends on your selection. Okay, this is basic geometry of MOS transistors. Both of them are legal. They are fine. Okay, the size is allowed. Okay, you can make it smaller. Okay, you can make it as big as the contact. Okay. All right. So right now, let's talk about the size. Right now, if we not only we need a minimal size, what if we need a bigger size? Okay, it's a single W. Right now, with a bigger, a fatter transistor, then this is the 4 times weight, 4 times larger. Okay. The larger of your width, okay, remember what I said before, the more contact you need to add over there, okay, because you cannot use a big hole, because the contact is exact. You cannot change the size. So the only way you can do is increase the number of contact. Use it as many as you can. Because the more contacts you use, okay, the less resistance you will create. That will give you a faster speed, okay, a smooth transition of the signal. It will be better. It will be better, all right? So mark down my words, okay? Use as many contacts as possible. Okay, now these are the design. Okay, this is the same design for inverter, but they have different design philosophy, totally different. Okay, you take a look left-hand side, the right-hand side. See that? This is the PMOS, because this diffusion is sitting in the red box. That means it is a P diffusion. That's P transistor. This one is outside the red box, so this is a diffusion. Okay. And check this out. This is the input, and this is the direction of the control current. So the current, the control signal, sorry. So the current goes this way, left and right. Okay, but for this one, it is fine. We use this way to do that. So the current goes up and down in the vertical direction. Either way is acceptable. It's up to you. My personal suggestion is the left one. Okay, it's up to you, but you like this one, fine. Okay, so this is a NOT cell or the inverter cell. Basically, they are almost the same. This is the layout. And don't forget the well contact. Don't forget the well contact. All right, so this is cool. There's nothing. All right, so they check the size. Right now, this size is not appreciated. Because if you check the size over here, you see that the width here and the width on the top, the W is the same. And the length is the same. So basically, you can see from these two figures, it's the same as well. They have the same W over L. Let me repeat again. For the P transistor in this design, okay, they have the same size, just like the N transistor. Okay, they are the equal size. It's a good one. Let's check it out. All right, now this is also the inverter design. The inverter design here, you check the size here. See that? This is the length. because this is the direction of the currents. So you check the size here. This one is smaller than the surrounding and the contact, but this one is equal. If you check the size over here, the W on the top is twice of the W in the bottom. So basically, this is 2W over one single L. This is a single W over a single L. And it's even more obvious over here. This is, if you compare the size of these two here, you can see that you have 2 times of the N transistor, and this is 4 times. So if you look at the layout, very quickly you can understand the one in the left, you are going to have a 2W over L for the P, and a single W over L for the N. This is one pair. And this one, you have another pair as a 4W over L. And over, the other one is 2W over L. Okay? Remember the homework assignment I asked you to do the first week? 2-to-1 ratio? That is why. Because we want to equalize the current given by the P transistor and drained by the N transistor. Because the mobility of the electrons is double of the, at least a double of the electro holes. So this is a correct, not a correct, a better version of inverter, okay, relative to the previous two. All right, is that clear? So the ratio here is correctly defined. They have to be 2-to-1. Okay, given that they have the same size, the same length. All right, is that clear? So this is a better version. Now we are going to check all the sizes of different logic gates. Okay, right now let's check. This is a NAND gate. Okay, let's check the size over here. Why the size is so different from the inverter. So let me put the inverter over here. So we have right now we have a very clear picture. What is the size for the inverter? So we know that we like to have this kind of ratio, 2W over W, or 2W over 1W. Now for the NAND gate, it's going to be this way because, I'm sorry, I gotta use the black marker. Okay, we know that NAND have 2 series. And then we have parallel. Okay? Remember I said that when you cascade these two together, let's assume we have a single unit of resistance over here. This will give you a single resistance over here. And because the current supplied by the 2W will be identical, almost identical to the current drained by the MOS. So we can assume that is also the equivalent impedance will be also the same. So right now, if we cascade them together, this is 2R will become 2R. That is bad. All right, that is bad. So what we do, we like to have similar sinking capability, current sinking capability. So we like to what? We like to make the resistance a little bit lesser than before. Then we become a single R. Become single R. So if we like to divide, divide the resistance into half, we have to increase the size, okay, from single W to 2W. That is why. Okay, that is why. So in this way, we are going to have the same current sinking capability like a single inverter. And because they are parallel, nothing will be changed. So the W stays the same. 2W and 2W. So this is why we are going to have, see that? It's a wider on the top, but right now we have to increase the width of the MOS transistor in the bottom to be double. So that after we cascade it together, then we are going to have the same sinking capability, just like that. All right, and we have two ways to do the layout over here. See that? Because the top part is not changed, the bottom of the input of the Y is slightly different. Here the input X stays the same, comes from the left, but the Y in this design comes from the right. Basically, this is not a good idea. So what we propose is that we like to place a port, input port, on the same side. So that will become this way. Okay? X, Y, okay, because they are inputs, they have to stand on one side, and the F goes to the other one. This is output. But that will create another problem. What is that? The poly signal, okay, of Y will have to travel a long, long way to the top. Long way to the top. And it is not appreciated in a high-speed design, because the longer the poly wire, okay, the slower the speed, because the polysilicon is a high-resistance material. That means it's a big R. Big resistance is not appreciated. So that is why, okay, when it comes to performance, it's not really appreciated in this kind of design. Anyway, right now it comes to another question is that how do we make it faster? And then it come down to your wisdom and your experience. How to make the layout arrangement much better than this one. Anyway, this is a doable design for you to understand. According to my experience, this one is is a little bit more appreciated, because the input and the output, they are sitting on different sides of the box. Okay, but that's one, even though that will give you a shorter polysilicon, but the problem is the input output will be messed up together. Okay, that's for the NAND cell. But the bottom line is, I like to bring this to your attention. Why the width of the MOS is increased? Because they are cascading together. You have to follow that rule to change the size of your transistors. All right. Okay, we are going to see a lot of more example. And what is this? This is a NOR gate. See that? We have two parallel transistors at the bottom, and we have cascaded PMOS on the top. So based on that rule, we like to equalize the current sinking capability. So the one, if you wanted to develop into the PMOS cascaded on the top, and then two MOS transistors in parallel, and this is NOR gate. Because they are parallel, nothing will be changed. So the W stays the same. But the problem here, we have cascaded the PMOS. This is R, this is R. We like to bring it down to become 2. So the overall sinking capability is the R, identical to the original one. So we like to reduce the resistance of each MOS. So the size must be increased by double. So it becomes 4W. So that is why we have very big fat MOS transistor on the top, because we like to increase the size to double. Originally we have 2W, right now we need 4, right? So that the current will be equalized for the rising edge and the falling edge. Is that clear? All right. And again, the input here is in the left, but this one really bad. sitting in the middle of the cell. That's a bad idea. So this one is better, right? Okay, but the problem is that the X signal have to travel for a long, long way to drive this one. Okay, so this is null cell. This is for the null cell. So basically, all the complicated cells can be designed follow the same analytical approach. Okay, if we are given a little bit more complicated rule or gates, is there any systematic way for us to follow to draw the design? Okay, here I show you a very a very old method, which is called a Euler path. Euler path, you all heard about it before. Euler path means that for any given figure, the figure is composed of vertices and arc. Okay, you are only allowed to use a single path to travel all of the arcs. For example, I'll give you some example. Okay, we have a figure like this one. These are called the vertex. This is called the arc. Is any way to draw this figure is only one shot. It's pretty easy. We draw over here and coming back. It's done, right? It's called a Euler path. In Chinese, it's called the 一笔画. Very easy to understand. Okay, you cannot take the pen out of the board. You have to finish it. All right. Now the next question is this figure can be done by Euler path? Can you find it? Can you find it? Is it possible, doable? The answer is yes, because you are all smart kids. So we do this way, it comes back, and it's done, right? Easy peasy. Even the undergraduate, even the kindergarten students can do that. Okay, that's fine. Now my next question is that let's use a Chinese word, which is the first character of your school's name. Can it be done by Euler path? Yes or no? Yes or no? Euler path, 一笔画. Can you draw this figure, the first character of your school's name? The answer is yes. I think the answer is yes. Is that right? The answer is yes. Okay? Then, how about the second character of your school's name? Can it be done? Can it be done? Can or cannot? Cannot. You're not smart enough, are you? Well, according to the Euler path, of course it's not. But a little bit of tricky part is that, okay, some sneaky boy, they might use this way, okay? Yeah, it's still doable. You're not smart, huh? Are you? Anyway, well, of course, this is not allowed by the Euler path rule. Okay? Of course it's not. So how do you make a judgment of whether this figure can be done by Euler path? Can anyone give me a rule how to find out whether a figure, a graph, can be done by Euler path? Come on, you are smart guys. You're great kids, so that you are allowed to come into this school. Have you watched the movie called the Interstellar? Okay, in that movie, Michael Mashu and Liv Taylor, I think, okay, they always say that there is a point, a single point inside a black hole. okay, that has an unlimited, super huge gravity. It's called a singularity. Okay, similarly, we define, okay, all the figure, we define the vertices and arc. If a single point has only one way to in or out, it's called a singular point, singularity. Okay, the point with the singularity, if over than 3, then this figure cannot be realized by a single Euler path. For example, here we have a singularity. This is only one way in or out. Number 2, number 3, number 4. 4 is over than 2, so it's not doable. But for this character, okay, how many singularity we have? 1 and 2. Here, this is 1, 2, 3, 4. It's odd. It's 4 paths. 1, 2, the odd number. Even number of paths. So it can be in and out. Okay, it's an even number. This is odd number over here. Odd number. Okay, it's an odd number, so this 2 equal to 2. So this is doable. And we have no singularity here, so this is doable. And if we have 3, this is a singularity, singular point. Okay, this is another one. We have 2 equal to 2. So as long as the number, the odd number of singularity is less than 2, okay, then it's doable. It can be done by Euler path. This is the Euler path rule. Why do we want to talk about this? Because we need it to do the judgment of whether a single strip of diffusion can be used to realize all of the gates or not. All right, let me give you some examples so you understand what I'm talking about. All right? Okay, this is a very complicated gate, okay, here. So again, we divide it into 2 parts. PMOS and NMOS. We care if it's about this one. It's NMOS. It's NMOS here. If NMOS is doable, then PMOS, of course, can be done. So right now, I'm going to need you to guide you through how do we make some judgment. Okay? We don't care about the PMOS right now. All we need is to take care of the NMOS, because the PMOS is the dual of the NMOS. So don't worry, I will tell you how to do that. So basically, we redraw the figure over here. We have a transistor over here. We have another 2. They are sitting on each other. So this is 1 over here. Okay? Right now, I need you some imagination to go through this process. So for the layout design, we always, this guy's very smart. I did not invent this, it's somebody else. Okay, somebody take the videos of Euler path to understand everything. Okay, for every transistor, it's replaced by an arc. This is an arc. Okay? And we have another arc over here. All right? And for the power supply and the output and all the nodes in between of 2 transistors is considered the vertex. So this one will be mapped to be a big arc over here, and another arc that's for this one and for this one. Please use some imagination. This is an arc. Arc, we don't care about the length, a single arc. And we have 2 endpoints. And this is transistor is equivalent to the arc with 2 endpoints. Okay, this is number 1, it's over here. And the output, okay, they don't have any transistor. They are short together. So a single point. And this is a power supply. There is no transistor. They are merged together as a vertex. So this transistor figure, schematic, is downsized to be the arc and the vertices. Okay, and then we follow the Euler path. Okay, we find there is no singular point because we have even number of paths getting out in and out. Even number. There is zero singularity. So it can be done by Euler path. If it can be done by Euler path, that means we only need one single strip of diffusion to realize all the transistors. Let me repeat again. If it can be done by a single Euler path, that means we can use a single piece of diffusion to realize all the transistors. That's a basic idea. So this is a bad idea. This is a bad design. This is a bad one, okay? And if we check, let me finish this one, we can call it a day. If we check the PMOS, it's the same. PMOS transistor, what we have? We have two parallel and one over here, right? Okay. So we have an arc, two arc, and the number 3 arc. So basically, this is reduced to be this way. Okay. How many singular points do we have? This is 1. Only one pass in and out. And this is 1, 2, 3. This is even. This is odd number. So we have 2. According to the Euler path definition, as long as we have the number of singular points less than 2, or less or equal to 2, it can be done. So that this can be done Euler path. Okay, there are several ways to do that. All right? So both of them can be realized by a single path, single Euler path. That means both of them can be realized by a single piece of undiffusion. That's all. So the next question is, right now we verified it. How do we do that? Now let me use the board over here to go through this. So first thing first, you make sure that you can find the Euler path. Then you have no trouble to realize it. So we start from the metal 1. This is VDD. Oh, sorry, VSS. This is GND, ground. Okay, because the Euler path theory told us that it can be done by a single piece of diffusion. So we just need a diffusion over here. Just a diffusion over here, all right? Okay, so don't panic. Then what we need 3 transistors. 1, 2, 3. 1, 2, 3. All right, 1, 2, 3. Now that's fine. Right now we need 2 in series. So these 2 are in series. So we need a contact here and contact here because these 2 are considered in series. So go down to the VDD. Is that clear? Right? And this guy, one side going to the output, the other side must go to the ground. Okay, so this one will go to the output. So this is for the P design. See, single piece. And you see how stupid that is? See that difference? Because this example show you if you don't follow the Euler path, you're gonna sacrifice a lot of spaces over here. Okay, and so stupid, see that? Because this is a short circuit, basically you can use a single diffusion to short them together. All right, Then we need, okay, a dual of a PMOS on the top. So basically, the ULA pass already told that it can be done by a single piece of diffusion on the top. It's done already. So right now, what we need is make sure that they are lined up perfect together. So for those two on the top, I'm sorry, I forgot the metal. Okay, we need a metal over here, all right? So basically, don't worry about it. Basically, we need a transistor, 1, 2, and 3. Sorry, make it smaller so that you can understand they are lined up together. Okay, so the one that in series must be dual on the top. So we got to make sure that one thing that this is goes to this way, and this one goes to over here. Yeah. So this one will be in parallel, go to, never mind, let me check over here. Make sure that they are correct. One side to the power, this side goes to the next one. Next one. Okay, let me check whether they are correct. Hold on a second. This one goes to the output over here. Okay, this is output, and what's left? There's only one thing left. Okay. Comes to, no, this is wrong. This one side goes to the other one, goes to, all right, don't worry. This one must go to, hold on a second, in serial. So the output goes together. So, okay. I'm pretty sure it can be done. Coming over here. Coming over here. Let's check whether this is correct. Okay, so for these two transistors, mapping to on the top, one side is cut to the power, the other one goes to the next transistor. This one is going to the next transistor, that is correct. And this one goes over here. Yeah, this is good. This is good. Okay, now the last thing you do is that you show them together. And show them together. That tells you one thing. As long as you can find a ULA path, just like the one I draw on the other board, okay, you can always use a single piece of diffusion to realize all the transistor. Why we do that? Because that will save you a lot of trouble. Okay, why is it a lot of trouble? Because you don't have to worry about okay, the sacrifice of area over here. You don't have to worry about how to align all the signals. Okay, as long as you take some practice, then you can get a very good result like this one. And this one, I will save you a lot of trouble to find out minimum number of tracks. The less tracks you use, the more area you will save. All right. So this is how we do that. My belief is this design is better than that one over there. Okay, it's better than the one over there. See, there are a lot of stupid connections. For example, the space here is no longer needed, and this one is no longer needed. Okay? All right? So my layout is slightly different from the one over there because I follow the Euler path theory. Okay, that will save you a lot of trouble. I use a single piece of diffusion to carry out all the transistors I need. All right, and before we close the session, so I give you some official definition. Okay, what is Euler path? This is Euler path. I just show you. Okay, in Chinese it's called 一笔画. As long as you can carry it out, that means you are going to have a single piece, straight diffusion check. You can realize everything. And CMOS logic gate graph is composed of vertices and the edge. Okay, vertices stands for the source and drain of the connections, just like this one. This is vertex. And the E stands for the edge or arc. It stands for the transistors, just like those over here. And each edge of the G is labeled with the gate signals, just like what I did over here. Okay, this is so-called the Euler path approach. All right, and the algorithm is the same as what I just said. The line of a diffusion rule, okay, find all the Euler paths covering the figure. Okay, find the P and N Euler paths, just like the one I just showed you here, that you can turn into the layout over there. If it is done, that means a single piece of diffusion is the only thing you need to realize all of the transistors. If you cannot find a single Euler path, you cannot find it, then break it. Break into a minimum number of places to achieve the step number 2. If you cannot finish the single Euler path, break it. Break it into as small as possible, okay, so that it can be done by Euler path. Then you have you follow the same rule. Use a single piece of diffusion to carry out the design. That is why. All right, so this is a rule how you do that. So this is one close to what I just did over here. See that? If you follow the Euler path, see, this is one, the same over here. And this is one over here. Okay, we have 2 parallel, just like these 2 over here. Then this is the last one on the top, over here. All right, so this is a better, more compact layout than the design you don't follow the Euler path. All right, enough said. I think this is the last thing I want to show you, I think, tonight. Okay, and you can take this home to do some practice. It's really complicated, okay? See that this is a composite gate. XW are the first one, and the output goes to the next gate. So this is a NAND gate. 2-input NAND gate goes to the 3-input NOR gates. Okay, and we don't have time for this one, but I will show you the final solution for this part. See that? This is an amazing answer. See that amazing answer? See that? Again, follow the Euler path. All you need is a single path, a single strip of diffusion for P and N individually, and it can be done. Because the Euler path told you that it can be done, then it can be done. All right? In Chinese, it's say, 只要能够一笔画，就一定做得出来. Is that clear? All right? We're going to talk about this example next Monday. So we called it tonight, and I'm really hungry. So we close it today, no homework, and that's done. All right? I'll see you next Monday.